I have a question because we're working on actually with crickets and some microclimates, and we're only just beginning. We started using a scalpel among other things, but we haven't actually done it in the wild yet, only in containers. Could you give any hints on kind of challenges of integrating RFID technology in insects?
Try to integrate them
with insects that are running around.
Okay, yes.
Jumping.
So what we've noticed is even if the weight is quite small, so people have demonstrated putting devices on these moths up to a gram. The moths themselves weigh a gram, and they have a payload of a gram. But it's not just the weight, it's also the form factor of the device. And so at this point, one of the big challenges is the antenna. The moths really don't like this antenna. It upsets their center of gravity, and it makes it difficult for them to fly. So actually one of the big challenges, in my opinion, is the antenna. What does that mean? Does that mean that we should think about moving up to much higher frequencies to be able to reduce the antenna form factors? I think that's perfectly reasonable.
All right, well, thank you.
Okay.
Moving on with platforms. So Matt Trotter is going to talk with us about the improved range of WISP tags using power-optimized waveforms. So I believe you're all set up, so take it away.
Thank you. I'm Matthew Trotter, part of the propagation group at Georgia Tech. We do research in RF power harvesting, and one of the new methods we came up with for improving the range of wireless passive sensors is called the power-optimized waveform. We tested this idea on the WISP, and we found some positive results. So in this presentation, I'll go over some background research in the area, talk a little bit about how power-optimized waveforms work, and then present the results. Range improvement research for the WISP is heavily related to range improvement research for passive RFID, since the two platforms are so similar. Well, the research area is very broad, and you can categorize it into two very broad categories as either on-tag research or off-tag research. So, for example, off-tag research would be figuring out how to communicate the tag in such a way that you get better range. On-tag research would be circuit design or antenna design or component selection, things like that. Going to the WISP, specific to the WISP, the research has been mostly on-tag. This morning there were some talks given on solar-powered, using solar power for improving the range, and then TV antenna broadcasts from Alanson. Well, besides those, most of it has been on-tag research. Better components using lower threshold diodes or diode-connected FETs improves charge pump efficiency. Better power management schemes using duty cycling and voltage regulation, and improved RF front end, so matching, antenna design. All of these researches have been performed, yet not a lot of attention has been paid to the communication scheme. So that's what this research aims to do. A power-optimized waveform is a waveform emitted by the RFID reader optimized for increasing the DC output power of the WISP charge pump by improving charge pump efficiency. So that's a mouthful, but essentially how a reader implements a power-optimized waveform is by adjusting the envelope of the continuous wave that it sends to the WISP for power. The objective here is to get a large maximum voltage without increasing transmit power. So, for example, you could adjust the envelope to look like this. So I've increased the voltage magnitude in the middle while decreasing it on the output, on the on the outer sides. What a power-optimized waveform, or a POW, as we like to call it, does is essentially focuses the power into very short, very strong, repeatable bursts of power. The WISP is a lot more sensitive to bursts of power than it is to a steady stream of power. So here's an example of a power-optimized waveform. This is called the Gaussian POW, and you can see why. It is essentially the CW modulated with a Gaussian waveform. For the same signal power as in the figure, the POW has a larger voltage magnitude in the middle, yet also has a longer time period. There are more examples of POWs you can make. It's a general kind of idea. You can have square wave POWs or sawtooth POWs or sinusoidal POWs, each having their own pros and cons. So what is the intended effect of a POW? Well, it increases charge pump efficiency. The charge pump in the WISP, just like the charge pump here, is based on the Dixon charge pump topology. And for power-limited situations, if you increase the voltage magnitude of the input, it increases the charge pump efficiency. So you can see the advantage for POW already. It has a bigger maximum voltage, yet it maintains the same signal power as CW. The POW also has an increased bandwidth. The figure on the left over there is the power spectral density of the example that I showed previously. The POW in blue has a Gaussian envelope centered at the carrier frequency, and you can see that for the same signal power, its power is spread out over frequency. The discrete subcarriers that make up the POW are spaced out by delta F. This is a subcarrier frequency spacing that corresponds to the inverse of the POW period. It's important that the POW period is short enough and the spacing is wide enough so that when you modulate the POW with data, the data spectrum does not overlap with itself, giving you symbol interference. POW period is also important for another reason, because it affects the envelope. The WISP uses a standard envelope detector comprised of a small charge pump, a diode, and a capacitor. The capacitor follows the envelope voltage of the transmission, and you can see for the CW case, the capacitor voltage in green follows pretty clearly the CW in red sent by the reader. The symbols by the reader are in the amplitude of the waveform. However, when you move to a POW, the capacitor hasn't changed, yet the POW period is long enough so it introduces ripple. So the capacitor discharges like normal, but you get this ripple effect. If the POW period is long enough, then the ripple can be so drastic that it falls below a decision boundary and you end up with a symbol error. So that has to be avoided. So that's a quick talk of all the basics of POWs. Now on to the experiments. The experiments we ran were two. We first ran a sensitivity experiment. This is just a proof of concept to show that it works. The next one was more formal. We measured POW gain versus transmit power. I'll explain to you what POW gain is when I get to it. The first experiment was set up like this. It has a custom transmitter capable of sending a Gen 2 query command with and without POW. We transmitted at a maximum of 15 dBm, and we had an adjustable attenuator that we could back off the transmit power. We set the WISP at a fixed distance away, and we measured the minimum amount of transmit power that was required to get a backscatter response out of the WISP. We measured the response using a direct conversion receiver connected to an oscilloscope, and you could clearly see the backscatter response on the screen of the oscilloscope or not. So the results are plotted in this table. They are mostly positive. We first tested a baseline of the Gen 2 standard CW. This is the way that most or all Gen 2 readers communicate with the WISP. It required 5.6 dBm of transmit power at 26.5 centimeter range. We then moved down to our first POW, the 1 POW. What this means is it has an envelope of 1 cosine of a very slow frequency. So this envelope is red, it's just a cosine. That required 0.9 dB less transmit power than the CW. So that's how you get POW gain. You could translate this POW gain into distance by transmitting at the same signal power and taking the tag farther away by 0.9 dB of distance. We then moved on to the 2 POW, and its envelope has a 2 cosine envelope. So it's cosine of 1 slow frequency plus cosine of another slow frequency, and it gives you that funky waveform there. When the cosines are aligned, you get double the amplitude of the 1 POW. So 2 POW has double the amplitude, 3 POW has triple the amplitude, 4 POW has quadruple the amplitude. And you can see as we move from 1 to 2 to 3 to 4, we get bigger POW gains. So going in, we hypothesized that this would happen, and we observed it. So that's a positive. We then got a little greedy and tried some Gaussian POWs. These have much longer time periods, yet they also have much taller peaks. When we tried it, they didn't work. It turns out that envelope detection was a big problem here because the peaks are spaced so far apart, and even though the WISP probably had enough power to respond, it didn't know when to respond. So that's a negative. But we then tried a square wave POW, which has a long time period, yet it produced a POW gain. This is due to the fact that the square POW has a much longer duration peak. So the capacitor